In this lecture, we will begin our discussion on chemical equilibrium. Before we jump into it though, we need to extend our knowledge of arrow conventions. The arrow that you're probably most familiar with is going to be the single arrow. The single arrow indicates that all reactant molecules are converted to product molecules. In other words, it's an irreversible reaction. The new arrow that we're going to become accustomed with is the double arrow. The double arrow indicates the reaction stops when only some of the reactant molecules have been converted into products. In other words, we have both directions taking place. We have reactants becoming products, and then we have products reacting with one another to form reactants. In terms of reaction dynamics, when a reaction starts, the reactants are consumed and products are made. We are familiar with this. At the beginning of every reaction, no matter it be one with a single arrow or double arrow, we're always going to end up with reactants reacting to form products. As the reactant concentrations decrease, the product concentrations increase. This is a result of reactants forming products. As the reactant concentrations continue to decrease though, that forward reaction rate is going to decrease. Why? Because we don't have enough reactants to react to form products anymore. Less interaction. Eventually, the products can react to reform some of the reactants, assuming the products are not allowed to escape. So in a closed system, in a perfect system, we can end up with these products, as mentioned earlier, reacting to form reactants. As the product concentration increases, the reverse reaction rate increases. Why? Because again, we have more interaction between those products. Processes that proceed in both the forward and reverse direction are said to be reversible. They are designated with that double arrow we discussed earlier. In a dynamic equilibrium, as the forward reaction slows and the reverse reaction accelerates, eventually they will reach the same rate. In other words, those two rates will be equal numerically. This is what we call dynamic equilibrium. This is going to be the condition wherein the rates of the forward and reverse reactions are equal. Think about those two half arrows of that double arrow. Once the reaction reaches equilibrium, the concentrations of all chemicals remain constant because the chemicals are being consumed and made at the same rate. Notice, at equilibrium, we have chemicals still being consumed and still being made. Okay, the only thing that distinguishes this phase is that it remains constant. But notice there is still change. That's why we call it dynamic equilibrium. An example of this is going to be the reaction between hydrogen gas and iodine gas, resulting in the production of hydrogen iodide. At time 0, when we mix those two reactants, there are only reactants in the mixture. So the forward reaction can take place and therefore will be the only rate that we will see. We also have our initial concentrations down here. Notice that we have no product. Why? Because the reaction has not begun yet. At time 16, assuming 16 seconds after the reactants have been mixed, there are both reactants and products in the mixture. So both the forward reaction and reverse reaction can take place. At time 32, there are now more products than reactants in the mixture. The forward reaction has slowed down as the reactants run out, and the reverse reaction has accelerated. Why is this? Because we have more products, therefore more interaction on this side of the chemical reaction. This is demonstrated in our concentration values below, where we see the products have a higher concentration than each of the individual reactant components. At time 48, the amount of products and reactants in the mixture haven't changed. The forward and reverse reactions are proceeding at the same rate. It has reached a dynamic equilibrium. Again, we still have reactions taking place. We still have the reaction pushing forward reactants to products and pushing back products to reactants. However, when you look at the bigger picture, you do not have change in concentrations. As the concentration of product increases and the concentration of reactants decrease, the rate of the forward reaction slows down and the rate of the reverse reaction slows up. So just looking at this image, looking at this description, we know that we're talking about the initial phase of a reaction. At dynamic equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction, and we can see this as two parallel lines. Again, just to emphasize this point, the rate of the forward and reverse reactions are equal at equilibrium, but that does not mean the concentration of reactants and products are equal. So that doesn't mean that they're not changing, and that doesn't mean that they're the exact same number. The rate is the exact same number, but the concentrations, they may be, but this does not indicate that they are. Some reactions reach equilibrium only after almost all the reactant molecules are consumed. Others will reach it only when a small percentage of the reactant molecules are consumed. This all has to do with the structure and dynamic between those reactants and products. A quick little analogy would be comparing this to population changes. So here we have two countries. We have one country with the initial population, right? We're going to consider these the reactants. And we're going to have another country that has the products, right? So initially we do not have as much going on that side. Initial, we have a net movement from A to B. Again, reactants to products. There are no products to be able to have a net movement from B to A. In equilibrium, after some time, immigration will occur in both directions at the same rate, leading to populations in country A and country B that are constant but not necessarily equal. Again, we're highlighting this point that the concentrations are not necessarily going to be equal. The populations are not necessarily going to be equal, but generally speaking, on both sides, they're not going to vary by much, and the rates will be equal. As with other concepts, equilibriums have constants as well. Even though the concentrations of the reactants and products are not necessarily, okay, it's not necessarily that they're never going to be equal, just not necessarily equal at equilibrium, there is a relationship between them, because remember, they are part of the same chemical reaction. The relationship between the chemical equation and the concentration of reactants and products is called the law of mass action. For the general chemical equation, A plus B yields C plus D. Of course, we have a double arrow, meaning that C plus D can yield A plus A. The law of mass action gives the relationship below. So remember, we're talking about this constant that's relating the concentrations together. The lowercase, now note that in this general equation, the lowercase letters represent the coefficients of the balanced chemical reaction. And we're always going to have products over reactants in this constant. So the way we write this constant, obviously constant is going to be K, because constant starts with the letter K. Excuse my sarcasm. And the actual, equation for it is basically going to be products over reactants. So we have the concentration of the products, in this case C and D, raised to their coefficients, right? Remember, these are the stoichiometric coefficients, so based on your balanced chemical equation. And this is going to be all over concentration of A times concentration of B, again, are reactants to the power of their coefficients. This is what we call the equilibrium constant. Notice what is the overall purpose. The overall purpose is to relate the concentration of the reactants to the products, because they're not necessarily equal, but they are related, because remember, they're part of one general chemical equation. This is unitless. I encourage you to do the math, plug in values, and realize why that's the case. But do not report K with a unit. Writing equilibrium constant expression. So this is the foreground. This is the basis, right? We're not dealing with numbers yet. We're just trying to write this constant that relates basically the concentrations between the reactants and the products. So for the reaction, now we have a real life reaction. We don't have A, B, C, D. 2N2O5 gas yields, again, double arrow, meaning that the products can also form reactants. 4NO2 gas plus O2 gas. The equilibrium constant expression is as follows. Remember, it's always going to be products over reactants. So what do we have down here? We have the first product, NO2, raised to its stoichiometric coefficient. It's the coefficient of the balanced equation, 4, times O2. Why doesn't this have an exponent? Because it's 1, right? Because our coefficient here is 1. But we generally don't write the 1 because it will not make a major difference. This is over the reactant, right? So concentration of N2O5 to the power of its balanced chemical equation coefficient. Why does the value of KEQ imply? So remember, K is going to be our equilibrium constant. KEQ, what are we talking about? We're talking about equilibrium here. So K is going to be your equilibrium constant when the reaction has achieved equilibrium. So at the beginning of a reaction like the ones we talked about before, those are not necessarily going to be, they're not going to have a KEQ because they haven't reached chemical equilibrium, dynamic equilibrium yet. But now, once we have a special K that we designate, and that's going to be called our KEQ. So when the value of KEQ, again, the equilibrium constant at equilibrium, is much greater, this is what these two arrows mean. One arrow, right, means greater, right? The two arrows is going to be much greater than 1. When the reaction reaches equilibrium, there will be many more product molecules present than reactant molecules. In other words, the position of equilibrium favors the products, which is why we're going to have more product molecules. So therefore, you can imply that when KEQ is going to be substantially less than 1, the position of the equilibrium is going to favor reactants because we're going to have many more reactant molecules present. So here we have an example of a equilibrium constant that's large, right? So substantially greater than 1. We're assuming that this reaction is left to continue until we reach equilibrium, and once we do reach equilibrium, then these numbers are going to give us a number that is greater, or a equilibrium constant that is greater than 1. Notice that we have this standard form in which the equilibrium constant is written in, products over reactants. This would be an example where the opposite is the case, where we have a small equilibrium constant. Again, we're talking about KEQ. Again, we have our products on top and we have our reactants on the bottom. You can notice that in the picture on the left, what do we see in the picture? We see not very many products, right? But a ton of reactants, right? So this is why we're going to have that smaller KEQ. So relationship between K and chemical equation. So when the reaction is written backward, the equilibrium constant is inverted. That makes sense, right? Because instead of having so in this case, our reactants would be our products. Therefore, they would be on top instead of on the bottom. So if this fraction is inverted, then whatever number we had would be inverted as well. So an easy way to convert between the two would be abiding by this formula. So if we're given a K of a forward reaction, the K of the backward reaction would just be 1 over that, the inverse of that. Why would that be the case? That's because of this concept that we just discussed regarding the ratio, right? So we have reactants being products, therefore they will be on top, therefore the fraction will be inverted, therefore our number will have to be inverted. So here we have another relationship between K and chemical equations. So if we're given A plus B yields C, we're familiar now that we would get this equilibrium constant. Now, if we multiply those coefficients by 2, it would reflect in this manner, right? Because that's where our coefficients play, right? They play as an exponent, therefore the exponent will be multiplied by 2. Going back to our properties of exponents, we can factor out that 2. We can pull it out in this form. Therefore, if you notice, you have 2 chemical equations, and in one, you've basically you've multiplied the coefficients by 2. Instead of recalculating the entire chemical equilibrium constant, you can just raise the constant to the power in which the coefficients were raised in. When you add equations to a new equation, the equilibrium constant of the new equation is the product of the equilibrium constants of the old equations. And we can see this here. So if we have two reactions, we have A yields B and B yields C, we get these two generic reactions. Now, if the overall reaction, assuming that these cancel, right? Because what do I mean by cancel? I mean that B is created in the first equation, but it's used up in the second equation, so we don't end up with any more B. So if we get that net equation is going to be A yields C. What would the equilibrium constant of that be? Well, it would be equilibrium constant equals products of reactants. So what happens to B? This is what happens to B. So what are we doing here? In a sense, we're taking the chemical equilibrium constant of that first reaction, and we're multiplying it by the chemical equilibrium constant of that second reaction. And that's what gives us this down here. So instead of doing all that, all you would have to do is multiply those two K values by each other to get that new equilibrium constant. Gases are unique, therefore they're also going to have specific properties that are unique to themselves. So the concentration of a gas in a mixture is proportional to its partial pressure. So as you probably remember in your previous classes, in some cases when you're using a concentration, you can use partial pressure in lieu of it, as long as it's constant throughout. Therefore, the equilibrium constant can be expressed as a ratio of the partial pressure of the gases. So in other words, if we have this general equilibrium constant, we can replace the concentrations with partial pressures, as long as that is done to every single one of the species involved. You cannot have a partial pressure here and a concentration here, right? The units won't, I mean, it'll give you a number, but that number will not be an equilibrium constant. Now, of course, if we're going to use partial pressures, we no longer are going to be dealing with Kc. So Kc stands for concentration. Up until now, we've been dealing with equilibrium constants that involve concentrations. But if we're using partial pressures to calculate the equilibrium constant, now we're dealing with Kp. P stands for pressure. When calculating Kp, the partial pressures are always in atm, okay, atmospheres. We will not be using torr, we will not be using millimeters of mercury, right? It's always going to be atmospheres. We standardize it by that, in that way, and that makes it so that we can complete universal calculations with that method. The values of Kp and Kc are not necessarily the same because of the difference in units. So notice, when we're using Kp, we're dealing with atm. When we're dealing with concentrations, we're dealing with most likely molarity. Kp is only going to equal Kc when you do not have a change in moles. So moles is going to be what's going to make these different, pretty much. Because remember, they are ratios, so at the end of the day, they should be pretty similar. The only reason why they wouldn't be similar is because the number of moles changes on both sides. So the relationship between them is going to be represented using this formula. This is directly proven with this formula. Why? Because if delta N is 0, what happens here? If we stick a 0 right here, this is all going to become what? This is all going to become 1. Therefore what? Kp equals Kc. In any other case though, Kp will not be equal to Kc. Why is that? Because we have a delta N. So now we have the derivation of that equation that was presented earlier. This is not a part of the course content, but in case you were curious, I have included it so that you can get an idea of how we got that equation. So we have this, and then we have the second part as well.